A queue in data structures is a fundamental abstract data type, ADT, that follows the first in, first out, FIFO, principle, meaning the first element inserted into the queue is the first one to be removed. This ordering mimics real-world queues such as lines at a ticket counter. Where the earliest arrival gets served first, the queue structure plays a crucial role in computer science because many system-level and application-level processes naturally require FIFO ordering for proper execution. Conceptually, a queue consists of two primary operations: enqueue, which inserts an element at the rear or end of the queue, and dequeue, which removes an element from the front. Other helpful operations include peek, or front, which retrieves the value at the front without removing it, isEmpty, which checks whether the queue contains no elements, and isFull, which applies to queues implemented using fixed-size arrays. The importance of queues arises from the fact that several real-time systems rely on maintaining the order of events or tasks, and a queue provides the perfect mechanism for such sequential processing. For example, queues are used in CPU scheduling where processes arrive and wait for execution, in disk scheduling, in breadth-first search, BFS, traversal of graphs and trees, in handling interrupts in operating systems, in printer spooling, in messaging systems, and in network packet management. Because the queue ensures fairness in handling requests, it becomes an indispensably fair scheduling mechanism. In terms of implementation, a queue can be constructed using an array or a linked list. Array implementation uses a fixed-size structure where two indices, front and rear, keep track of the positions of the first and last elements respectively. When an element is enqueued, the rear pointer is incremented, and when an element is dequeued, the front pointer is incremented. However, traditional array-based queues suffer from a problem of unused space because once front moves forward after dequeuing, the earlier positions cannot be reused unless the queue is shifted manually, which is inefficient. To solve this issue, the circular queue or ring buffer was introduced, where the array is treated as circular, and both pointers wrap around when they reach the end of the array. This ensures that the entire allocated space can be reused efficiently. In the circular queue, the queue is empty when front equals rear, and full when rear plus 1% size equals front. This technique optimizes memory usage and is widely used in embedded systems, operating systems, keyboard buffers, and data streaming applications. On the other hand, linked list implementation of queues is more flexible because it grows dynamically without requiring a fixed-size array. A queue can be implemented using a singly linked list by maintaining two pointers: front, which points to the first node, and rear, which points to the last node. During enqueue, a new node is created and attached to the rear, and during dequeue, the node at the front is removed. Linked list queues avoid the issue of overflow unless system memory is exhausted and ensure efficient O(1) time for both enqueue and dequeue operations. Furthermore, queues implemented using linked lists allow for simpler expansion and contraction, making them ideal for applications with unpredictable input sizes. They are also easier to implement for more advanced queue structures, such as double-ended queues, DEQs, or priority queues. Beyond basic queues, several advanced variations exist. The double-ended queue, often referred to as a DEQ, allows insertion and deletion at both the front and the rear. This makes the DEQ a more versatile structure, supporting either FIFO or LIFO behavior depending on how it is used. DEQs are central in sliding window problems, scheduling, and implementing algorithms such as the Aho-Karasik string matching algorithm. Another important variation is the priority queue, where elements are removed based on priority instead of FIFO order. A priority queue can be implemented using arrays, linked lists, binary heaps, or advanced tree structures. The priority queue is widely used in algorithms such as Dijkstra's shortest path, Huffman coding, and event simulation systems. Although priority queues deviate from the strict FIFO rule, they are considered an extension of the queue concept and showcase the flexibility of queue-based thinking in problem solving. Queues also play a vital role in graph traversal, especially in breadth-first search. BFS. BFS explores nodes level by level, and a queue ensures that nodes are visited in the order they are discovered. The queue stores adjacent nodes of the current node and processes them sequentially, enabling BFS to find the shortest path in an unweighted graph. Similarly, queues are used in level order traversal of binary trees, where nodes are visited level by level. In operating systems, queues manage process scheduling, where processes waiting to execute are stored in a ready queue. Interrupt handling also uses queues to process hardware events in order of arrival. In networking, packets arriving at a router are stored in queues before being forwarded, ensuring steady traffic management and preventing packet loss. In multiprogramming, multiple queues are used to maintain fairness across different job types, leading to multi-level queue scheduling algorithms. The mathematical analysis of queues falls under queuing theory, an essential field in operations research. Queuing theory studies the behavior of queues under different conditions, such as arrival rates, service rates, and number of servers. Models like MM1, MMC, and MG1 explain how queues behave in communication networks, call centers, and distributed computer systems. These models help predict waiting time, average queue length, and service efficiency. Thus, queues are not just programming constructs. They are analytical tools used to model real-world systems. From an algorithmic perspective, queues are extremely efficient. Both NQ and DQ operations take constant time O(1), making queues ideal for time-sensitive applications. The memory performance depends on the implementation. Array-based queues require contiguous memory, while linked list queues use scattered memory but allow dynamic expansion. Circular queues offer a hybrid benefit by solving the space reuse issue of linear queues. Queues also support concurrency and synchronization through thread-safe implementations. In multi-threaded systems, queues serve as communication channels where one thread produces tasks and another consumes them. This producer-consumer pattern is fundamental in operating systems, parallel processing, and distributed systems. Languages like Java, Python, and C++ provide built-in concurrent queue structures that ensure safe operations in multi-threaded environments. Another important application of queues is in simulation systems, such as traffic light simulations, airport runway management, banking systems, and server request handling. In these systems, events must be processed in the order they occur, and a queue provides the ideal mechanism for representing event flow. In caching systems, queues are used in least recently used LRU and first in first out FIFO cache eviction policies. The simplicity, efficiency, and versatility of queues make them essential for foundational understanding in computer science. They teach critical concepts such as order management, resource allocation, scheduling, synchronization, and memory optimization. Whether implemented through arrays, circular structures, or linked lists, queues remain one of the most indispensable data structures, providing structured solutions to problems ranging from system-level operations to high-level algorithm design. Their ability to model real-world waiting lines, control execution flow, and ensure fairness across operations highlights their continuing importance in both theoretical learning and practical applications.